Hello, class. So in this video, we'll continue on section 3.2/4.1. In the previous video, we just introduced just a reminder of what an nth order linear differential equation looks like and what an nth order linear initial value problem looks like. And we saw a theorem that was very similar to the one we saw in section 2.4 about when are we guaranteed to have a solution and in fact a unique solution to an initial value problem. And as we saw in an example, and as the theorem says, not only are we guaranteed a unique solution, we know that it exists on this exact interval. Contrary to the nonlinear case we saw in 2.4, when we didn't know exactly on what interval the solution existed, only that such an interval existed, okay? So now let me introduce a new piece of notation. A linear, so again, as I mentioned, we're only going to be talking about linear differential equations from now on. A linear nth order ODE of the form, right, so the same form, and I keep forgetting to write a naught of x here. Right. The same form as a nth order linear ODE as we saw before, it's homogeneous if whatever is not being multiplied by any derivative of y, which you usually write on the right-hand side, is equal to 0. Right, so what's the nth order linear ODE? Look at this at general first order linear ODE. Whatever's on the right-hand side of the equation, which is the same as whatever is not being multiplied by any derivative of y, including y itself. Remember, y itself can be thought of as the 0th derivative. Then whatever is not being multiplied by any derivative of y has to be 0. And again, if you've seen calculus, if you've seen linear algebra, well, it's the same sort of thing as a matrix equation being homogeneous, right? It's an equation set equal to 0. Okay. So let's see some examples. So a differential equation like this, t squared times dy dt, so let's see the second derivative, plus dy dt 4 equals 0. So this is second order because we have a second derivative. It's linear because whatever is multiplying the derivatives are expressions only of constants and the independent variable, which in this case is t. And anything that's not being multiplied by a derivative, which we usually write on the other side, is just equal to 0. On the other hand, this differential equation this one is not homogeneous. Why? So it's still second order and it's still linear. The reason why it's not homogeneous is because, again, whatever is not being multiplied by any derivative of y, including y itself, has to be equal to 0. But here we have something that's not being multiplied by any derivative of y, and it's not equal to 0. It's 7. Right? So this one would be not non-linear. So this one is not non-linear, non-homogeneous, sorry. So this one is homogeneous. This one is not homogeneous or non-homogeneous. Either way, I usually write non-homogeneous. Okay? So it's as simple to check as that. Okay? Look at whatever is not being multiplied by any derivative of y, including the function y itself. If that's not equal to 0, then it's not homogeneous. Now, since I'm only working with linear differential equations from now on, anytime I say homogeneous, just to save space, anytime I write homogeneous, I'm implying the differential equation is linear. Right, so I could just say something like, we have this second order homogeneous differential equation. Okay? I will say that, and then you have to immediately think, okay, that means linear. So anytime I say homogeneous, it's also going to mean linear. It's not necessarily the case, right? In terms of a differential equation being equal to 0, I don't know if they call them homogeneous in the literature. They might. It might be that homogeneous is only reserved for linear differential equations like I'm going to do here. However, in the definition I gave you, I say that a linear nth order ODE of the form like this is homogeneous. I'm not saying that a homogeneous one is necessarily linear, but for our purposes, anytime I say homogeneous, I'm also implying it's linear. Okay? So I'm going to drop the linear from now on, again, because every differential equation we work with from now on is going to be linear unless I specifically state otherwise. So please keep note of that. Now, let's start with one of the craziest theorems. And again, this only works because we're working with linear differential equations. And so there's a homogeneous version, which is the one we're going to see first. And then we're going to see how to extend it to the general case, where we have a general nth order linear differential equation, not necessarily homogeneous. But again, this is crazy that this works. Now, I'm not going to prove this theorem. It's actually kind of easy to prove. So I'm going to have you do it in the homework, just to get you some exposure of how proofs work, how mathematicians and anyone that's working in more theoretical things try to make things as general as possible. So it won't be hard, and I'll give you hints, but just know that there is an easy proof for this, and you're going to do it in the next homework probably. Okay? So this is called the superposition principle for homogeneous equations. Again, homogeneous means that they're also linear. Okay? So let y sub 1, y sub 2, all the way to y sub k be solutions of, not the, I don't know why I keep saying the, of a homogeneous nth order ODE. Again, it implies it's linear on some interval I. Another thing I mentioned before I started talking about the last few topics, Euler's method, phase portraits, and direction fields, was that now I'm going to focus a lot more on the intervals on which the solutions are defined. Okay? So now I'm going to start putting this into basically every definition I give and every example I do in terms of solving differential equations. I'm going to actually find on what interval does the solution work. Okay? So here we're given k solutions to an nth order homogeneous ODE on some interval I. This is the crazy thing. If we combine the solutions in this form, so if we write a new function y as a sum of the k solutions that we know are solutions, where we can multiply each of these solutions by an arbitrary constant, doesn't matter what it is. If we define a new function like this, it turns out that y is also a solution on I. Now, to me, that's crazy because if you think about it, given any random differential equation, there's no reason that just because you know two functions are solutions, that their sum is also a solution. Why would that be the case? But there's no reason for that, unless your differential equation is linear. Again, that's the most important thing. Again, also we're working in this case with homogeneous ones, but we'll see how to extend this to non-homogeneous differential equations. But this is crazy, and again, this comes from linear algebra. So you will recognize this from linear algebra, where this is replaced by a matrix equation. Okay. So really crazy stuff. Now, an expression like this, when you take a sum of functions, each multiplied by arbitrary constants, we called such a thing a linear combination of the functions. Okay. So we would say that y is a linear combination of y1, y2, up to y sub k. So anytime I say something is a linear combination of these other things, so in this case, if I say y is a linear combination of y1, y2, up to y sub k, immediately think of an expression like this. That always means that y is equal to an expression like this. And I'm omitting the parentheses x because it's obvious from above that these are functions of x. And the c sub i's are constants, right? Right, so this is what a linear combination is. Please get used to this notation of linear combination. Why? Because I'm going to use the word linear combination a lot from now on, okay? So again, whenever you hear the word y, it's a linear combination of other functions, immediately think of this equation here, immediately. And again, it's crazy. It's in general, this is never going to work. But the fact that this is a linear homogeneous differential equation more importantly, linear, it makes it that, well, that this actually works. Given any solutions that you have, a sum like this is also a solution. So let me give you an example of what something like that would look like. But in terms of, just for the sake of keeping the video short, I'm going to show you an example in the next video. Okay? And in terms of why this works, I'm not going to prove it, but what I want to do is I'll give you a sort of reasoning why this kind of works, but I have to build up for that reasoning. So I don't think I can do it yet. Okay? So I'll show you an example in the next video.